Let's study the reaction of ozone to form oxygen. Ozone is O3, oxygen is O2. They're both just made of oxygens, and I've drawn something like what their structure might look like. So the ozone molecule has these strong single bonds and then these weaker bonds between the oxygen molecules. We could also draw this using a resonance structure, but I'm not going to do that right now. And that makes this molecule ozone more unstable than its close cousin oxygen, which is held together by two pretty strong covalent bonds, a double bond right here. So before I go any further, let me make sure I have a nice balanced formula. So we have, I'm going to put a 2, coefficient of 2 in front of the ozone, and then in front of the oxygen, I'll put a 3. So 2 times 3 is 6 oxygen atoms. Here we have 3 times 2, that's also 6 oxygen atoms, so this is our balanced equation. Now this might seem like a simple bimolecular reaction with a rate law that would say negative d concentration of ozone divided by dt equals reaction constant K times the concentration of ozone squared. And that's because we might think that there are two ozone molecules just hitting each other and forming this. However, it's found through experimentation that the reaction does not follow second order kinetics. That's what we get when we have an exponent of 2 up here. So we have to come up with a reaction mechanism that might explain the kinetics of the reaction. Now, a reaction mechanism is a set of elementary reactions that might explain the kinetics of the reaction. So just another sort of terminology thing, an elementary reaction is a single-step reaction. So here is one proposed reaction mechanism, and it comes in 2 steps, 1 and 2. So the first reaction has ozone in a sort of fast equilibrium, that's what this back and forth arrow means, with a forward rate constant of K1 and a backward rate constant of K negative 1. And so this goes to an oxygen molecule and an oxygen atom. And the second step of the reaction says that we have an oxygen atom running into an ozone atom to form 2 oxygen molecules. Again, this is molecular oxygen, this is ozone, and this is atomic oxygen. And the second reaction has a rate constant of K2. It's sort of found that the first reaction is called our fast reaction, or fast step, or rapid equilibrium. And then our second reaction is our slow step. So if you sort of imagine this reaction mechanism like a pipe through which some water is flowing, the first part of the mechanism, it would be like a bigger pipe. So the water could freely flow through that. And then it encounters this sort of smaller part of the pipe, so the water can't flow through quite as quickly. So that means that our slow step is also our rate determining step. And what I mean by that is that we're going to write the rate law in terms of this slow step. Before I get to writing that rate law, let's just check one thing out. We want to make sure our equation balances. So on this side of the 2 reactions, we have an ozone molecule, we have an oxygen atom, and we have another ozone molecule. And that is going to an oxygen molecule and 3 oxygen molecules. I'm sorry, this is an oxygen atom. So just like in algebra, we can sort of cross out like terms on either side of that are on both sides of the equation. So we can cross out these 2 oxygen atoms since they appear on both sides, and we can also combine like terms. And this gets us back to our original reaction, which says that 2 ozone molecules react to form 3 oxygen molecules. So our reaction mechanism here in 2 steps does agree with our chemical equation, so that's a good sign. And now let's get to writing the rate law for this reaction. So as I said, we write the rate law in terms of the slow step. So that says that our rate is going to equal the rate constant, K2, remember that's given here, times the concentration of oxygen atoms times the concentration of ozone molecules. and these are both to the first power. And that's sort of in agreement with our elementary reaction here. We can't actually write a rate law in terms of a reaction intermediate. That's what this oxygen atom is here. So we're going to have to do some math to figure out a way of sort of getting rid of this oxygen atom in our rate law. So the way that we can do that is by writing the mass action formula for the first reaction. This is our fast reaction. So we see here this is these two-way arrows indicate that this is in equilibrium. So we can say that KEQ, that's our equilibrium constant, is equal to the concentration of oxygen molecules times the concentration of oxygen atoms divided by the concentration of ozone molecules. Again, this is our mass action formula, and what mass action formulas tell us in general is that there's some equilibrium constant, KEQ, that's equal to the ratio of the products over the reactants. So what we're going to do is we're going to solve this equilibrium expression for the concentration of oxygen atoms, which is the same concentration of oxygen atom that appears here in our rate law. So in doing that, we arrive at the concentration of oxygen atoms is equal to the equilibrium constant, KEQ, times the concentration of ozone atoms divided by the concentration of oxygen molecules. And so what I'm going to do with this concentration here is I'm going to plug it into our rate law right here. And so now we can rewrite our rate law. And so that's going to say the rate is equal to our reaction rate constant, K2, times KEQ times the concentration of ozone atoms divided by the concentration of oxygen molecules. Sorry, I said ozone atoms, I meant ozone molecules. Divided by the concentration of oxygen molecules times the concentration of ozone molecules. Just to sort of re-explain how we got to this new rate law, this sort of funky looking one, we took our rate law from the slow step, the rate determining step. We said our rate, that's the same, equals K2, that's the same, times the concentration of oxygen molecules. And here we have all this stuff in the place of the oxygen molecules, and we arrived at that by using our mass action formula here and solving that for the concentration of oxygen molecules and plugging that in here, which is why we have all this business going on here. And then finally, we have our concentration of ozone molecules. So we could actually rewrite this rate law and combine like terms and combine these constants here. So we get rate equals just some k, and again, this k is this right here, times the concentration of ozone molecules squared, because these two concentrations times each other equals the concentration squared, divided by the concentration of oxygen molecules. And so this is our rate law for this reaction. One more way that you might find this rate law, is the rate equals K times the concentration of ozone molecules squared times the concentration of oxygen molecules to the -1. And mathematically, these are two equivalent expressions. And let's just sort of go over this rate law to see if it sort of makes sense in terms of our reaction here. And also going over our reaction mechanism to see if it makes sense. So we know that ozone is unstable because both of these two oxygens down here are competing for this bond. That's sort of what this dashed line bond means. So because of this, we might call it even a partial bond. That's not a very scientific term, but that's an all-right way of thinking about it right now. Because of its partial bond, it can break apart easily into an oxygen molecule and an oxygen atom. Ozone is unstable. And then if we add more oxygen to the system, we would see that the rate would decrease. And that sort of makes sense because of Le Chatelier's principle. which can be interpreted to say that increasing the amount of the product's oxygen would sort of force the equilibrium towards the left, would cause the reaction of ozone to oxygen to slow down and even cause it to sort of go backwards. So our reaction mechanism and our rate law are in agreement with Le Chatelier's principle. And then finally, this oxygen atom here is pretty reactive, and it would react with ozone here more easily than it would oxygen because, again, the bonds in ozone are not very strong. They're kind of weak compared to the pretty strong double bond, this double covalent bond here in oxygen. So we might expect it to react more easily with ozone than we would with oxygen. So again, that's in agreement with our proposed reaction mechanism and our rate law here.